Yeah. Thanks for coming here. There's a reason I wanted to give that talk, and that is that a lot of things currently going on in IT security seems to focus on the attack side. And the reason is attacking, our computers are fragile. That's essentially the problem. Attacking is simple because so much can fail. And defending is hard because you have to essentially find every bug in the system to prevent it from being exploitable. So situations like this, yeah, you go to your favorite party or not, and someone from CCC was already there. Or you go to a large news organization and find fake messages. And that's the harmless cases. It gets worse, like our government is complaining the Chinese are breaking into the computers. And of course, it's not just the Chinese breaking in just the Germans' computers, it's everybody breaking into everybody else's computers. Yeah, even the guys who are supposed to know about security, like the scene, the lead hackers, like the backtrack people or the exploit database, they get hacked. And oh, that was all last week, wasn't it? It's impressive. So there are people running around saying defense is dead. And well, it certainly looks like it is in a way, because everybody is hacking everybody else. And so is that really true? And I think the answer is no, not quite. That's the wrong picture. That's the right picture. It's that's poor IT security after the riot, still heavily drunk. So if you go outside and try to spend money on making your computers more secure, what you get is this. You get a $30 billion market of IT security products. Products like hardware, software, and consulting, right? Probably some guys here making the living on it, some selling virus scanners and firewalls, some telling people to install virus scanners and firewalls. And that's half of the frigging market in IT security. Virus scanners and firewalls, it doesn't help against anything, right? So if it used to help 10 years ago, these days there's a directed attack, and it will bypass your firewall because you have to open it to fetch your mail. It will bypass your virus scanner because somebody wrote that exploit just for you, and you're toast. So it's a market. I understand why people do this, because there's money in it, but it's not really giving us any real security. So the question is, why are our computers broken? What's the problem with the security we have? And I think the central problem is that there's a huge difference between academia and the know-how we have on one side, and the outside reality of computers on the other side. Because what we're using is, like, you're either using Windows or the one or other variant of Unix, right? If you look at the history of those things, you'll figure out Windows, or the Windows we're using today, Windows NT, used to be VMS. VMS was written by a guy who read the Unix source code because that was available at the university as a pirate copy. And the model is the same. And Unix was written by two birdy guys who had the problem that their boss was telling them not to play too much games on the main Multics machine, because that had billing. The term account came from accounting. They actually built the computing time to your account, and so your boss had to pay for it. And they wanted to play games, and couldn't explain the money to their boss. So I thought, oh, we're going to write our own operating system, right? Hacker style. We're going to do it ourselves, like as a joke, because we can. And for that reason, they named Unix Multics. And they stole pretty much of the concepts from Multics. And like the address separation model. People back then realized computers crash. So you would write your assembler program, your computer would crash, and you would fix your assembler program, and it would keep crashing. To the point where they invented that stuff, where you could have multiple users emulating crashing machines all at the same time. So your process could crash without affecting my process that crashes, right? Big progress. So actually, they advertise for that fact. So that picture is an actual picture from an advertisement for Multics, and you see there's a ring, and because they introduced the ring concept of security. That's what we are still using. So stuff like, I use a high-level language for writing by kernel. It's also something that Multics pioneered, and that Unix and NT VMS are doing as well. It's no longer assembler in the kernel. It's like I'm using C, a high-level language, or in the case of Multics, I think it was APL. We have processes, and it's still the idea, well, it will crash once in a while, and if it crashes, you know, we restart it, it boots fast. So virtual memory, another concept from back then. So essentially, the security concepts we're using, they're 40 years old. But progress hasn't stopped. There is actually no reason why a program should ever crash, given what we've learned in the last 40 years about, you know, type systems, about how to build compilers and everything. It's entirely possible to build secure systems using what we've learned since. And what I'm trying to do in my talk is to give you a rough idea of what those people out there dabbling in that stuff are doing. So what are current projects in that direction? Is it any good? And is it transferable to, you know, like real-world problems? Like back then, when I was at university in the mid-90s, I dropped out of it after 2 semesters. But back then, we used to do proofs of program correctness, right? If you prove your program to be correct, it doesn't have any bugs. If it doesn't have any bugs, it doesn't have any exploitable bugs. Yeah. So we did that like 5 lines, and we did the proof manually, and it wasn't formally verified. And then I dropped out of university and came into the reality of shipping products out there, and nobody ever cared about proofs. Yeah? If you would invent a new algorithm that very, very, very rarely happens, in a situation where that algorithm is critical, somebody might sketch a proof. But that's it. Nobody ever proved something to be correct, and I thought, you know, learning about verification of program correctness was a total waste of my time in university. Turns out it's not. But I'm getting to that later. So what's at the core of our security problems right now? If you go to CVE and look at the bugs that appear, you quickly figure out that the really majority of those problems falls into a couple of categories. Like, you know about memory corruption, buffer overflow, buffer doesn't get properly checked, and you overrun something, and then you do extremely interesting stuff to exploit it, which is an art form in its own right. But for our way of looking at it, all that happens is that I access a buffer with the wrong index. So it might be that I have a stack overflow or a heap overflow. It might be an integer overflow, which leads to a buffer overflow in the end. It's all memory corruption. The second big field of where do problems come from, heap semantics, right? I free something twice, I follow a null pointer, I use something after it was freed. A very interesting bug that many people do not know is a zero size allocation. If you pass 0 to alloc, you might get back a valid pointer. So checking for null as a return value does not mean it's safe to write into there. So another big problem. Third class, it used to be, well, you had race conditions in shell scripts for quite a long time. The recent OpenSSL bug is the first one I've seen where concurrency issues inside the binary were used to manipulate a process in terms of actual code injection. But it works. So cross-thread semantics is something that, if you've ever done any parallel programming, you know it's pretty ugly to get your locks right. You have either deadlocks or you have race conditions, and you have situations where those race conditions lead to security problems in terms of executable code, in terms of, you modify a value in some structure that allows you to do things you're not allowed to do. The fourth one, it's becoming pretty big. It's 10 years ago, nobody has ever heard about cross-site scripting. These days, it's the only thing the kids learn because it's so easy. And of course, you always have this stupid user problem, right? So let's look at those in turn and see what we can do. Memory corruption. The big problem is that programs are written by humans, and humans make mistakes. So for a block of 1,000 lines of code, you're guaranteed to have a bug in there. If you want to get rid of memory corruption issues, you have to make sure that the mortal programmer never gets within reach of the ability to do memory corruption. So essentially, if you're starting a project in C now, using language C, without any really convincingly obvious good reason, you're a fucking idiot. Somebody will break it. Somebody will do a modification, and you overrun a buffer. I think there are 2 or 3 persons in the world that can write C code without introducing buffer overflows. I think 2 are at the conference. Go to DJ Bernstein later, he's cool. But most people, including me, I do not trust to write C code that doesn't have any buffer overflows. And I trust me even less to get all that, integer coercion right and overflow situations and everything is just a mess to handle. I can probably do it when I focus on it, but when I write code and I have a deadline, I do not want to focus on it. So the only thing you can do is use language that allows you to come up with an abstraction. You might have heard about the concept of abstraction. It's absolutely great. It's your primary tool as a programmer, as an engineer, as a mathematician to get things right. Abstraction. So you introduce an abstraction where you bounce check every buffer access. Easy, right? What's the problem? Right, performance. Somebody said performance back there, yeah. The modern approach to this is to make the compiler a bit smarter, to give the compiler the ability to reason about integer ranges. I'll get to how you're doing that back later. But for now, you write down an abstraction that says, here's how you access a buffer, and there's my bounds check. Of course, you have to make sure you have the bounds everywhere, right? You have to pass them around. Then the compiler comes and sees, oh, wait, I can prove that the integer will be in range 0 to 10, and I know that that area has 16 bytes, so nothing bad can happen. It will actually optimize out that bounds check. You can look at that in GCC. They're a bit failing because they fail to properly represent ranges when they wrap around, so there are situations with integer overflows where it breaks. But essentially means step number 1, you come up with a good abstraction that completely eliminates that class of bugs, right? What we've seen, those 5 items, okay, the 5th one is a bit of a joke, but again, I come back to that later. From those 5 items, the 4 represent more than 95% of all security problems out there, all the exploits you can download. We can completely eliminate complete class by just doing the right thing. Heap semantics false. Basically the same story. It's like if you cannot trust your programmer to call malloc and free, right? Just make sure they don't have to call malloc and free. Come up with an environment in which memory is automatically managed. Java, yeah. You can say a lot of bad things about Java, but the good thing about Java is that it got garbage collection into mainstream. Like you want to have a garbage collection, you want to have some piece of code that makes sure that nothing bad happens, because the user doesn't say free. He might say malloc in a way or another by constructing objects, but it never says free. I have a piece of code that makes sure that free is called at the right instance and not sooner, not later. That was somebody who said performance. I've heard that. I've heard you. The good news is that garbage collection and memory management is a research field in its own, and they did marvelous progress in the last couple of years, up to a point where there are situations where you can show that manual memory management is less efficient than automatic memory management. For instance, because you have to call malloc and free inside a tight loop, and with a garbage collected system, you can just now collect the garbage once you're out of your tight loop, and will be by orders of magnitudes faster. And it might be a bit slower in average in practice. The old problem is if you ever use Emacs, it will stop for doing garbage collection. Garbage collectors don't do that anymore these days. They don't stop, they're incremental. They're able to run on multiple processors. So essentially, if it is a performance problem for you, you can do 2 things. One is put in another processor and put your garbage collector thread there. Or idea number 2, the same fucking thing you would do in C in a real-time operating system, because in C, memory management is not real-time hardened, so you have linked lists. And in order to avoid that, you use static buffers, right? If you write a real-time operating system, you need a defined answer, you use static buffers. You can do that in your garbage-collected language as well. So there are ways around the performance problems. It's a known field of engineering in its own right, but you can get rid of all security problems related to the user not properly calling free. Cross-thread semantic faults. That's a very good one. There are people who say that it's just an incredibly stupid idea to have shared state across threads, because it becomes a big nuisance and a big hassle, and very, very soon. And the one or other might have heard about the Erlang programming language. It's a very successful functional language, once invented by Ericsson. And those guys are the telco engineers, right? So they want reliability. And so decided to write their programming language in a way where there's no shared state possible at all. So you cannot just access the same data structure from two threads, because the language doesn't allow that. If you want to have two threads doing work, you have to communicate via messages. And that's obviously safe. So it might still stop, so you might have to do an analysis on your state machine whether it will continue processing in all situations. But it will never lead to a situation where, due to a race condition while accessing the linked list of something, you suddenly have a situation where you control a pointer that gets called as a function pointer in the next step and be exploitable. Closure is another language you might have heard about that's following a similar idea. It's even harder. You don't have any way to modify the state of an object. So, and you might have heard a little tendency this is going into. And I think that's the big realization in it, that designing your programming language is an essential step in designing a system that's overall secure. Right? If you start out with fundamentals that are inherently broken, you can do what you want on top of it, do all your procedures and testing, and if it works to get rid of all those bugs, it will be very, very, very inefficient to write that code. If you write, for instance, C code according to the specifications you need for airlines, for air industry, for people building planes, you end up with a process where the programmer writes 160 lines of C code per month. The rest of his time he's spending writing documentation, doing analysis and everything and everything and everything. So if you're not having adequate tools to do the abstraction you need, you'll end up doing lots of work. So the engineering you're doing for your total system is designed to give you both the abstraction you need and the power to actually get done with that stuff in your project. In-band signaling. Oh, that's my favorite one, because one day I realized that SQL injection is essentially equivalent to blue boxing, because you have a signaling path, and you have the signaling inside your user data. So I don't know how many people remember blue boxing. It's like when you had a whistle and blew into your phone and it would do 3 calls. It was a little bit more difficult, but something like that. Same happens here, right? You insert a semicolon or a single quote, and that suddenly becomes part of the SQL statement. It turns out there are instances of that are easy to deal with, and instances that are difficult to deal with. And the actual blue boxing is an instance of that's really difficult to deal with, because you need to install filters. But when you install filters, the audio will sound bad. So you can only tune up the filters up to a certain point or introduce active filters. So it's really, really hard to come up with a filter that's both safe and not a problem to the user. There are instances where it's very easy to do something about, like SQL injection. If you have an SQL injection in your code, somebody should beat you with a clue stick. Really, like you use prepared statements and everything's fine, because there will be an API that does that transformation for you. So instead of assembling, the SQL statement yourself, you put placeholders in, and you call functions for saying, that's the value of my placeholder, that's the value of my placeholder, and it will be safe. this can be extended. The concept can be extended if you have a language that has a properly powerful type system. Because you could come up with a notion of a string that's not just a string, but you say this string is properly escaped to be inserted as a value in SQL statement. You can even go a bit further. Like if you look at the grammar of an SQL statement, for every production in that grammar, you can come up with a conversion routine that converts a string into that type of grammar production and be safe. So once you have that in place, you can have a system where you cannot just pass a string. You have to pass a converted string, otherwise you'll get a type error. If you introduce stuff like that, you will be able to prevent those kinds of work, like all the cross-site scripting stuff. There are frameworks in Java that actually work pretty well doing that. So even with low-level tools like Java, you can do some stuff like that. And that's really a problem. But even there's things you can do. For instance, if you do not want something to happen, and you have a system where you can write down your "I do not want this to happen" as one line, as opposed to I have to check hundreds of thousands of lines of code whether that happens or not, then it's easy to deal with that problem, because once you realize that users are stupid in a certain way, you can come up with an answer for that certain way. Okay, sounds all good, right? There's an if. Okay, I have the garbage collector who's guaranteeing me the garbage collector is working right. I might have an implementation that checks for buffer overflows. Who knows whether that is right or not? I have code that does transformation on the code I've written there. Who guarantees that the assembler, the compiler outputs, is equivalent to what I wrote? Etc., etc., etc. So it turns out that there's something called the trusted computing base. And now that's my lines of code that I actually rely on for everything else to be consistent and working and fine. And this code requires extra attention. And you want your trusted computing base to be as small as possible, obviously. Like if you have the Linux kernel or the macOS kernel, and you have a Broadcom chipset, and you have that 2 megabyte Broadcom binary, and that fails, your kernel will crash. So the trusted computing base inside a Mac or inside a Linux is the complete kernel, because every single line can step on every other single line's toe. If you want a computer that's safe, that's secure, you need to come up with an overall system architecture that reduces the trusted computing base down so much that you can actually sit down, read it, understand it, and trust it. So the thing is, ordinary people can't. You as a hacker have a chance of understanding the trusted computing base. That's the difference. But nobody here in this room would be able to understand the whole Linux kernel and the security implications of every single line. That's simply not possible. So what can we do about that? There are different approaches, like I've talked about formal verification and proving of stuff being correct. That's what you need in order to build systems that work. There are two approaches currently. One approach is I'm writing preconditions and I'm writing postconditions into my code. You might have heard about that. This code assumes that when you pass in a linked list, that eventually it will end a null pointer or something, and it will return a list that has the same property. So preconditions, postconditions, invariants. You might have heard about that. And there are two approaches. One approach is having the computer come up with the proof itself. Like you give it all your data and it says check or no check, and then you start modifying your code until it says everything's fine. And the other approach people are using is proof assistance. Proof assistance, the computer doesn't even try to come up with the proof on its own, but it automates working with proofs for you. And you can tell it in what direction to go into. So if you end up writing a proof in that, it looks like, hey, I want to do an induction on that list, and then I want to use that hypothesis and substitute that, and I'm using the lemma of transitivity, etc., pretty much manually. SMT solvers, I've going to look into that. You probably all know that, right? It's first order logic. You have propositions like today is Tuesday, or it's raining outside, and they can be true, like today is Tuesday, or false, like it's raining outside because it's snowing outside. And you have and or, and not, and implication, so from A follows B. And you have quantification. You can use the for all operator and the exists operator. So you can say, for all objects in my heap, they do not overlap. Or for all pointers in my system, they will always point to the beginning of a properly allocated object. Or there exists a foo so that blah, 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 blah. That's first order logic. So the SAT problem is the satisfiability problem. You probably remember, if you did any computer science, your complexity theory, and you probably run across NP-complete problems. So that's what they told you. That's a hard problem, right? It turns out in practice you have NP-complete problems or harder problems all day, and you're using heuristics to solve them as good as you can. It's the same for satisfiability. So the problem is, given an arbitrary expressions, find values that make that expression true. And when you extend that using mathematical objects like natural numbers, floats, lists, something like that, you end up with something that's called satisfiability modulo theories. So you have a satisfiability problem like in the last step, and you have a sort of data objects and properties you have on them, and ways to solve that. So you basically throw in your expression, say solve, and it will give you values that come out of that. There are quite a number of them because they're a very pretty hot research topic. The one that I want to mention especially is the Z3. Not because it's better or worse than any of the others, I do not have an opinion of that, but because Microsoft took it and integrated it into a C compiler. So they have a C compiler where you can do annotations with preconditions and postconditions, and that uses SMT solving to tell you whether your pre- or postconditions are true or false. And if they're false, it will fail to say this is okay. And Microsoft has actually spent an insane amount of time and money onto writing a verified hypervisor. Like Hyper-V is there, you probably all know that stuff. What they are trying to prove here is that it will work according to a certain security specification. So say a security specification can be something like, I do not have any buffer overflows. Or in the case of Hyper-V, it means if you have different address spaces and different processes running there, there's no way to access the process space of another process. I do not think that address spaces are a good security model, but yeah, anyways, that's what they do. So you write code that looks like this. So it's basically C, and you have invariants in there. So that's a definition of a data structure. And you give additional invariants. Like the arrow here is implication, like we had that. So if this is true, then this will be true. So that's an invariant. When modifying the data structure, you always have to make sure the invariant holds. And the SMT solver needs to find a proof for that, and it doesn't find any proof for your code must be broken. Well, except that, as I said, SMT solving is equivalent to SAT solving. That's an NP-complete problem. So we do not have any way to always come up with the right answer. And so if it says, I cannot prove that, it might be that your code is buggy, but it also might be that you just happened to hit a bad spot in your proof process, and it won't find a proof even though there is one. Yeah. So another example, here you see code, a function. You have keyword like requires and claims and ensures that pretty much handle your invariants and your predicates. So the atomic section, for instance, is something that's executed atomically and that is allowed to violate the environment given up there outside, inside, but it will always be correct outside. So this will then pass. Your development process looks like this. You write your C code, you annotate C code, you put it into the VCC, and then it either says it's wrong or it just keeps running and doesn't find any answer at all because equivalent to halting problem. You all know that story. So at some time you press Control-C, look at the log, trying to figure out what went wrong by applying your intelligent magic on what's essentially a crash dump. So the thing why many people do not think that's the right approach is because it's very, very manual. Like you're still using C, right? You still have a chance to code a buffer overflow every 5 lines. Just that now you have the tool to prove every 5 lines that your buffer access is okay. And I promise you, if you do that, you'll never get done. It's like for any real-size project. Microsoft had the opportunity to throw like 50 people on it for a couple of thousand lines of C code, so that works. So you have to be smarter than that. And that's where higher order logic comes into play. Higher order logic is another layer of abstraction. As you do not only have propositions, but you have propositions about propositions. And that allows you to do abstraction. Like you can say what it means for a relation to be transitive, and then you can later say this relation is transitive, which you couldn't say if you couldn't talk about relations. In SMT, you can only write down relations. You cannot operate on them. And now, that's the stuff that's really blowing your mind if you're dabbling into proofs, because that's where suddenly power comes from. You probably have a rough idea of what a type is. Even if I do not go into lambda calculus and type theory, you have an idea what a type is, right? I write down some expression in a language, and if that expression is correct, it will have a certain type, like integer or float or string. A dependent type is a type where I say my x is an integer, but the following property holds, colon, like x is an integer between 0 and 5, or x is an integer between 0 and a parameter L, where L is a parameter that I've passed to the function. Of course, that, I have an x and x is prime. This, of course, gives me a much, much finer control over the handling of data and the handling of things I'm passing around. So instead of writing down for every single function that the parameter x I'm passing in has a certain property as an invariant, I can come up with a type that encodes this information. And the interesting thing is that we are starting to blur the lines here between stuff that happens at compile time, stuff that happens at runtime, because in a dependent type, what you write down as the x, which holds the following proposition. The proposition, again, is code. So you're using code inside the type specification that gets executed by compiling it. But the really mind-boggling stuff is the Curry-Howard isomorphism. Anybody ever heard about the Curry-Howard isomorphism? 1, 2, 3. You have. Sergey, raise your hand. You know what that is.
I heard about it, I don't know.
I'm going to explain that to you, because it's very, very fundamental result. So we are dealing with proofs here. Like, we want to do verification. We want to see our code is correct, so we're proving it doesn't have a certain bug. It turns out that if you look at code in lambda calculus, and I should explain lambda calculus. How many of you know what lambda calculus is? How many of you can explain lambda calculus in one sentence? That's amazing, because it's fucking easy. If you write down f of x equals x times x, and you want to calculate f of 3, then you substitute the 3 for the x's, right? That's lambda calculus. It's simple substitution on arguments. Everything else is bootstrapped from that. You can build booleans from that, and numbers and everything. You will add a theory to come up with different kinds of x, because dealing with functions that return functions gets boring. So you come up with what's called an inductive calculus, saying, you know, a natural number is either 0 or the successor of something, and you throw that into that. And so you have expressions in lambda calculus, and you have the types of those expressions. And it turns out that you can write down mathematical proofs in lambda calculus, where the theorem you're proving is the type of that expression. So checking the type of a lambda calculus expression is equivalent to checking whether a proof is right. And the objects you're using are the same. So if you apply that, it means that you suddenly program in a universe where your code, the types of your code, the propositions about correctness of your code, and the proofs for that all live within the same universe. And you can reference them to each other. You can assign them to a variable. You can build a structure where you have a parameter x and a proof y. You can pass that around. You can construct proofs from the proof you got in, et cetera, et cetera, et cetera. So that's really, really powerful stuff. So there are different kinds of proof assistants out there. The first one was ACL2. I actually worked for a while on Lisp compilers. ACL2 is written in Lisp, and one of the customers asked us to come up with a better implementation of the hash table because they had a 150 gigabyte hash table. Turned out that customer was a semiconductor manufacturer who does validity checking for his processors, and every second one of you has a processor from them in your computer. So that's actually in use for quite some time now. They're not all the same. The Bryan criteria, I think I have to explain that. That has to do with the trusted code base of my theorem prover. If you use ACL2 or PVS, you essentially have to trust the complete code of your proof assistant to be correct, because every transformation can change something, so every transformation has to be mathematically correct. But you remember the Curry-Howard isomorphism thing? So writing a proof is equivalent to constructing something in lambda calculus that has a type of what I'm trying to prove. So what you can do, and what those people do, is they have a so-called proof kernel. That's nothing but a type checker for lambda calculus that checks whether the proof is okay. And then you have tons and tons of code for automating your proofs, like search strategies and optimizations for different cases and everything, like different tactics that you're using and applying. And you only have to trust that one single type checker for your proof to be okay. So that's the de Bruijn criteria. And if you look at that, it's pretty obvious that Coq would be the tool of your choice. I'm coming to that. But first, let's look at another project that did formal verification. That's the L4.verified microkernel. Probably you have heard about the L4 kernel. It's pretty popular in Dresden and in Karlsruhe. And also in Australia, it turns out. And those guys came up with a formally verified L4 kernel. So they have a formal proof of correctness of all the API functions, essentially giving you, again, properties like, as a process, you cannot look into another process's address space and everything, so separation. What they did, that development process really sucked. Yeah. They wrote a model of what they're trying to achieve, like an access control model, what's allowed, what's not allowed. Then turned that into a high-level design. Basically, turned the properties they wanted to achieve into a model of something that achieves those properties, proved equivalence, more or less, and then came up with a Haskell prototype. They actually had two teams operating on that. Very interesting from the engineering perspective. They had one team writing the microkernel, and they had the other team doing the proofs. So what the team did was, in the first step, write a Haskell prototype, of which they then proved that it would behave like they wanted it to behave. And then they wrote another implementation of it in C and proved equivalence between the C implementation and the Haskell implementation. They wrote something like 120,000 lines of proof for an 8,000 lines microkernel. But they did it, yeah. You have to admit they're good, they achieved the goal. It's just not the way that I would like to write more than 8,000 lines of code, right? Because that step, that's something a compiler can do for me. I do not want to do that manually. So I think this is the biggest achievement that is out there in terms of verified code, of formally verified systems, CompCert. It's from the French guys. Anybody here who's from France? University? You've heard about that stuff? Not? That's awesome. So those guys came up with a formally verified, optimized C compiler. Formally verified means they have a semantic model of what C is doing, which turns out to be hard to begin with, because if you open up like your Kernighan-Ritchie, and every second line says this is implementation defined. So GCC1 used to call nethack if it hit something that's implementation defined, until the user said, no, it's not okay. But they came up with a formal specification of what their C is doing. They have written down, that's the next problem, that you do not have formal semantics of what the instructions on your CPU are doing, because that won't be given to you by the manufacturer. But they wrote down a specification of the assembler instructions, and they have 7 transformation steps that transform C into lower and lower languages until the end of this assembler. And for every step, they have a formal proof of correctness of that, that compiler step. And they can assemble the thing in the end and give you one huge proof. So it turns out to be a huge proof inside, but it's only a couple of lines calling all your functions, because you end up writing your proofs like you write code, with functions that you call, etc., levels of abstraction. And they've shown that they can do that. And there has been a working group that did fuzzing of C compilers. So they generated valid C code, and then they gave it to GCC, LLVM, and CompCert. And they found hundreds of bugs in GCC, surprise, and found hundreds of bugs in LLVM, and there were only 11 bugs in CompCert. Those turned out to be in some piece of auxiliary code in the parser that's not inside the proven code yet, and they get very red in the face and moved that code there and did the proofs, and now it's fixed. So it's now giving 0 bugs if you fuzz it. And that's the level you want to achieve. And yeah, so that's all nice and good, right? You can obviously write, oh yes, and they've been using Bogk because it's the most powerful tool out there with dependent types and higher order functions and everything. Now, what somebody should do is take all that mathematical and computer science technology that's there and apply it to real-world computers, right? Build a computer that from scratch uses those principles. That's, of course, a lot of work, and it turns out that a project like that exists. It's DARPA funded under the CRASH program, and they're actually designing the CPU in order to get something which has a formal definition and everything. The programming language, or in fact 2 programming languages, and the operating system. Because only when you do that, and that would probably be a topic of another talk, only if you do all that together, you can not only maintain your security goals, but you can also reach the performance goals. So lots of people involved. So what's the goal? And it's their words, I copied that, and it's pretty bold statements, like game-changing. Suddenly we have defense. Suddenly we can build secure computers. That's the promise. And it's designed to make it easy to write secure software. Like your users are stupid. If they write something, then they should usually hit the right spots so it will be safe. And for really critical problems like memory corruptions, etc., you want to have it in a way that it fails in a pleasant way, like giving you an exception, the process being cleaned up and restarted, etc., etc. They want resiliency to attacks. That's if you break a Linux kernel, it crashes. You reboot your computer. What they want is to give every piece of code as little access to everything else as possible. And they have a couple of things that need hardware support in order to make it fast. So how are they doing that? I think I've explained the rough idea of using formal verification tools to come up with code, of defining what the problems are, and so that's their idea. They want to have a very fine-grained compartmentalization. That's both done on a language level. The programming language should make sure you cannot access something you don't want to access by not giving you primitives to allow that, by enabling semantic boundaries, but because you can never be sure, also enforcing that boundaries on a hardware level. The concept is stolen from the Lisp machine. I don't know if you've ever looked into those architectures, but there you couldn't write a virtual memory address into the DMA controller because the virtual memory address has a different type tag than the physical address. So it just won't work. You try to write to a virtual address and it says no type error in hardware. I think the real goal of that thing is showing that engineering of something like that in large scale is feasible. So coming up with good engineering strategies for writing proofs. And yeah, that's a lot of food. I think it's better to explain that. The process they're building, it pretty much looks like you're on a processor. Yeah, you have a program controller, you have registers, you have an arithmetic logic unit, you have memory. Some things are different. First thing you'll notice that's different is this. That's a type tag. So the idea from that Lisp machine, actually it's the same guy who built the Lisp machines at MIT, Tom Knight, who's doing the hardware design for that. And you have a type management unit. And you can not only are there hard-coded types, but using the type management unit, you can use virtual types, so you can come up with as many types as you want. And B, you have principles. So principles, and that's where coming back to the beginning of the talk, are the equivalent of rings, just that it's no longer ring 0 or ring 3. So principle is the logical entity on whose behalf the code is executing. And this can get arbitrarily fine-grained. One example, you have a browser, and you have a plugin API for that browser, and you have a password store in your browser, and you want that plugin to be able to fill out a form for you by putting your password into the right field. How do you prevent the plugin from getting access to your password? Well, in ordinary systems, you can't. In this system, you can say that the principal plugin just doesn't get access to that area because it will fail in hardware. And that's after all the stuff we did for proving our program to be correct and after using language theory to make sure it will never actually happen. If it does happen, it will fail. So the idea here is to come up with a regular system where you have a immutable hardware. Then you have an abstract machine that behaves as if you had arbitrarily many type tags. And you have OS services on top of that. And then on the top, applications. So one thing, where's the kernel? Answer, there is no kernel. Kernel is a stupid concept. Everything's the kernel, right? You have your pieces of code, and they only need to interact with each other. Why are you doing all that, abstract machine with the type tags? Because you can do interesting stuff with it, like provenance encoding. What's that? Say you have two different kinds of networks. One you call secret, and the other one you call I can download Lady Gaga CDs here. You maybe realize that your users are stupid, and you want to have a rule that says, data from that secret part should never go onto that Lady Gaga CD. Using provenance encoding, you can use a bit in the type tag to encode whether that data entered the system on the secret or on the non-secret interface. And you can specify that no secret data should ever leave the non-secret interface, and hardware will enforce that for you, hardware in the abstract machine. So I've said no more kernel. You probably cannot imagine an operating system without kernel, but it works. If you think about embedded systems do not have a kernel either. It's all code running there. And of course, if it crashes, everything crashes, but we made sure it won't crash on a semantic level. So it's no problem putting everything into the same address space and leaving the kernel concept away. And using other means of separation than having ring 0 and ring 3, kernel and user end. So every single thing that does computations on my machine should be only have access to the data it needs to have access to, and it should only be able to execute what it needs to execute. So basically you do compartmentalization, which is very, very flexible down to one word. So you can set up the machine, if you call it a function, all the memory it will ever see is its stack frame. It cannot write anywhere else because there is no other memory than the stack frame. Down to, yeah. So it's obvious what the goal is. You want be able to decompose your system into verifiable units. And you want breach containment. If you have a breach, nothing bad shall happen. So there's a problem with composing proofs and everything. That's if you have two systems that are easy to understand, like cars. Like everybody understands cars, and trains. Trains are easy to understand. But put cars on a train, you're getting a car train. What happens? The alarm in the car goes off, and the car goes like beep, 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 beep. So that's an effect of, it's not that easy to compose systems. So it's probably infeasible to verify the whole system. But the idea is to verify those parts that absolutely critically need to be verified, and to give you the tools to verify interesting properties even at the higher levels. So, oh yeah, I like that one. Byzantine complexity, it's a term they came up with. And it's essentially the number of subsystems, of security-relevant subsystems that can fail so that your total system will still be secure. You see, we're leaving the domain of mathematics here. We're into engineering. Everything can fail. My hardware can fail. My software can fail. Every line of code can fail. I can have come up with a proof that's stupid. Like if I have stupid code and a stupid idea of what the code is doing, I can prove the stupid thing to do stupid things. And that doesn't help me any. So that can happen, even if it's very, very hard, but it's still possible. So the attempt is to defend against all that, like non-bypassable forensic trails, another instance. Like you cannot shut it down because there's no root account to shut down the forensic trail because it's hard-coded in there. It's a bit tricky to do debugging in a system like that. So debugging is, again, a property that you really need to think really hard about in your system design. Here's an example of how they think that should happen. And this is how the SAFE project thinks about to implement a scheduler. So instead of having the kernel with the scheduler, you have 3 compartments. And the scheduler compartment has access to all the states, and it decides on what's the next runnable state. And it communicates using message buffers with the dispatcher. The dispatcher doesn't have access to the state, but the dispatcher can say, make that thread runnable or not runnable, and it gets passed back from the scheduler the next runnable state, and you can execute the state, right? And then you have the alarm clock, and again, the alarm clock is your, it will interrupt the next, interrupt your process, schedule the next one, but it won't do that directly, because in its compartment can only say, time's up, and it tells the dispatcher compartment, hey, time's up for that process. So the dispatcher compartment tells the scheduler compartment, hey, time for that process was up, can you please give me the next thing? So you have distributed your system across 3 independent instances with very defined interfaces. And so that's the idea of compartmentalization, of a need-to-know principle in a machine. Yeah, so my career advice, become a proof engineer, because those will be needed. Because people are spending $30 billion per year on snake oil, like virus scanners and firewalls. And they would gladly pay you $30 billion if you build working, secure computers. So that's a good, the URL is a good introduction into that field. And if you really feel like that's the thing for you, those SAFE people are still looking for PhDs to do work on that. The project is financed for 4 years. So check them out if you want to go into that. Yeah, because we're taking over the world. Thank you.
Are there any questions?
Oh yeah, we have 5 minutes for questions. That's not.
Hi. I just wonder, because what you have presented is really, I mean, is really nice, because, you know, you prevent a lot of errors. As you said, it's 95%. But at the end of the day, the problem, I think, really is defining security. So what do you mean by security? And this actually applies very much to some things that you said were snake oil, because at the end of the day, the virus scanner is trying to decide if you really wanted to run that application, and because the application might be, you know, a virus, or it might be, you know, just Microsoft Word or whatever. And the thing is that you cannot, you don't know how to define that is a virus and define that is Microsoft Word. So at the end of the day, you know, you can have all these compartments and all of that, and prove more or less all your executables. The problem is, once this gets out and everybody's trying to use this, you know, you will eventually have to define what you mean by security. And, well, and if I'm receiving something from my friend and says, you know, hey, run this, this is my new program, you know, this is my new executable, I just, you know, patched it. How do I know?
I understand the question. Let me give the answer to that. So, how do I define security? I do not define security as something absolute. I define security in terms of security goals that I want to reach. And I do not want to be susceptible to buffer overflows. Is already a security goal that would get me much, much further than I am today. Like, you can open up PDFs again without worrying. Imagine. And so I probably won't be able to come up with the definition of a virus and say my system will be virus-free. But I do not need that. I can define my security goal is that none of my secret documents will ever leak out of that interface. And the thing about, you know, running somebody else's program, I think the answer is just do not bother with binaries at all. So the interface for other people's software is source code with proofs. And if it doesn't fulfill my self-defined security goals, it just won't compile. So I have no interest in defining what a virus is or not. I just have the interest to prevent my stuff from leaking. And if your code leads to my stuff leaking, my compiler won't compile it. So that's the idea behind it.
Hi. I have a question. Is there, about a year ago, I was searching, is there any hardware implementation for interpreters? For example, hardware JavaScript.
Well, why on earth would you want to do that?
Yes, because interpreters, they have, how can I say?
Well,
okay,
let me answer differently.
I wanted to ask you, what do you think about that?
Well, I do not like interpreters too much because I like security, but I still like performance. But you do not need interpreters to reach what you do with interpreters these days, like a high-level language, like JavaScript. You can compile it. You can have interactive JavaScript execution by compiling it. In fact, nobody's writing JavaScript interpreters anymore. If you look at Firefox, that's all JavaScript compilers. And of course, in a system like that, you could define, if you have a semantics of JavaScript and semantics of the machine, you can write a compiler and prove your compiler to be correct and execute JavaScript on top of it.
Okay, I just wanted to ask whether you know the Verve operating system from Microsoft Research. It's from the Singularity project.
Yes.
They built a type-safe operating system with typed assembly language, and they have it working. They have a working, I think, scheduler. But are working on proofs for
I've heard about Singularity, and I even know that it's in production use, which Microsoft doesn't officially confirm, but it exists. And yeah, I couldn't have talked about all possible projects there are that go into that direction, because that list would be endless. But yes, it's something like that. It goes into that direction, using type systems to do interesting stuff. It's just that Haskell's type system isn't powerful enough to do some of the stuff that they're doing in Bogk, using dependent types for proofs. You have no proof assistant there. So essentially, again, from an engineering point of view, you're not writing your proof and your code at the same time. You're writing two different things, and I don't like that too much. But yeah, Singularity is cool. It's a nice project.
They also had the solution for the problem, for example, when you load JavaScript onto your computer, that the program gives the proof, proof is attached to the program that it works correctly and doesn't harm your computer, and you can just verify the proof for that program, and so everything is safe.
Yeah, you mean proof carrying code? Yeah, proof carrying code is another field I haven't even mentioned yet, that you ship your proof of correctness with your binary. It's an interesting idea, but the fact that you can actually have formally verified compilers, as shown by CompCert, that's much stronger than just proof carrying code.
JavaScript is compiled in bytecode, but not that bytecode is not readable by the CPU.
I'm sorry, you can compile JavaScript into assembly instructions, believe me.
No.
Yes, you can.
No, you can't.
Yes, you can.
Okay, I could prove that you can't.
You do not need bytecode in the bytecode interpreter. You can always compile it down to machine code.
No.
Every language, yes.
No, I can prove that you can't. No?
Oh, we should have the discussion afterwards. But
Okay.
Okay, one last question, and then I think we wrap it up.
Yes.
Two? Okay.
I have a practical question. Mm-hmm. Okay, so the framework exists for building secure systems, mm-hmm. but what you do for the legacy code base which exists, does this
legacy
mean
applications? Well, I put unsecure machines on my network that's protected from the real world using my secure computer. So yeah, I run old stuff on old computers. That's the answer to the legacy problem.
Because okay, we can build secure systems if we build them from scratch. But,
yes.
But if the users need legacy applications.
Yes, they should buy a second computer for the legacy applications. That's what I'm saying. Because otherwise you cannot build secure computers.
Thank you.
Okay.
Hallo.
Yeah.
I have noch eine Frage. I have a question. What about the military projects? For example, they use ADA or they use some military operating systems that are so approved in some way because they do not want their rockets to fail and stuff like that.
Most projects I know about are not on a level. If you look at common criteria specifications, you'll find that the highest level of common criteria only requires you a proof of correctness of the model of the code. It doesn't require proof of correctness of the code.
But they have certified compilers and they are quite costly.
Yeah, it's all classified, but it's better than the stuff out there, but it's not playing in that league.
Okay,
they are coming up with good results, but it's a lot of manual work, very tedious work, and they're paying a shitload of money for engineering that stuff. Something we can do.
Would you recommend to use ADA instead of C? Instead of C?
I don't like ADA. But I like it more than C. If I had to choose between ADA and C, I would write ADA, but it's by no means powerful enough.
Hello, we have a question from the RSC channel. Herpele wants to know, doesn't security end when we share data with unsecure computers on the internet or send data through unsecure nodes?
Well, the worst they can do is DDoS you, right, if your computer is secure. So, yeah.
You have time for one more?
I think you should wrap it up.
Okay, thank you.
Okay. Thank you again.